In the last video we studied the limiting process, so we kind of got a better idea of how to determine a limit. And so in this video what we're going to do is we're going to focus on limits at infinity. So when the independent variable either increases without bound to positive infinity or decreases without bound to negative infinity. And really the idea of computing these limits at infinity is really what is the end behavior of the specific type of function. Okay, so the first thing we're going to look at is when the function is a polynomial. From module 0, we actually remember that we know what polynomial end behavior looks like. Okay, so if the leading coefficient, so remember a sub n refers to the leading coefficient, if that's positive, well, we have to know two things. We have to know the leading coefficient and we have to know the degree. So n is the degree of the polynomial. So if, for example, if the leading coefficient is positive and the degree is odd, then it's going to decrease without bound as t goes to negative infinity. So as it goes further and further left, it's going to decrease to negative infinity. And if it's going to the right, it's going to approach positive infinity. And then, for example, if the leading coefficient is negative and the degree is even, it's going to decrease in both directions to negative infinity. Okay, so for an example here, we have the limit as x approaches infinity of the function that is minus 5x to the fourth plus 6x cubed plus x minus 1. So if we go through and do this limit, really what this is saying is that when we look at a polynomial, its end behavior, or it's to find its infinite limit, all I'm concerned about is the leading term. So I could, in essence, say this is equal to, this limit, its value, is equal to the limit as x approaches infinity of, well, going through here, the highest degree term is this one. So I can just say this is going to be equal to, in value, to 5x to the fourth, negative 5x to the fourth. Okay. I'm going to come back and make an important note here in a minute, but let's go ahead and finish this. So as I look at this, the degree of this is even, okay, so I'm in this column, and the coefficient is negative. So that puts me in this case up here. So as I approach infinity, so as I go to the right, it decreases to minus infinity. So this is actually minus infinity. All right. Now I'm going to put my note in red here. Okay, so going from here to here. This is not, so I'm going to also put a little triangle here. This is not saying that the polynomials are equal. The polynomials, and I'm just going to say polys, are equal. Okay. It is saying, however, the limits are equal. Okay, and so really for any polynomial, as long as I know its leading term, I can determine its end behavior, and consequently its end behavior is going to tell me its limit. All right. So we're going to use this idea again when we look at rational functions. Remember that rational functions behavior, as you go out to infinity or minus infinity in either direction, it's going to approach the horizontal asymptote. Okay, so if we can determine the horizontal asymptote value, if there is one, that'll tell us then behavior. Okay, so remember, to find the horizontal asymptote, we have to know and p and x here are both polynomials. That's another restriction. So if the degree of p, the numerator, is n, and the degree of q, the denominator, is m, then and the leading coefficient of each of them is a and b respectively. Okay. So really what we can say is that this looks like ax to the n plus dot 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 something, and then probably plus a constant a0 or something, and then up here this is bx to the m plus dot 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 plus another constant all the way down to a constant. Okay, so really I'm just again looking at the leading term in both the numerator and denominator. So if n, the numerator degree, is greater than m, there's no horizontal asymptote. If it's less than, then we have a horizontal asymptote at 0, and then if they're equal, it's the ratio of the leading coefficients. Okay, and so this correlates directly to the limits. So again, if we have p over q and we know that n is greater than m, okay, the limit here is actually going to be plus or minus infinity. Because if it doesn't approach a horizontal asymptote, it's clearly either increasing or decreasing without bound. We'll need to determine that. And that's fairly straightforward to do once we get there. If n is less than m, then that's in this case, well, our horizontal asymptote is at 0, so our limit's also going to be at 0. And then if they're equal, then it's actually going to be the limit is still going to be that ratio of leading coefficients, a over b. Okay, so then lastly, if we look at this example here, so I have two polynomials. This one has a degree of 5, this one has a degree of 4. So the degree of the numerator is greater than the degree of the denominator. Okay, so it's going to be one of these forms of infinity. But how do we decide which one? Well, let's do that. Let's look at the approximation that we did with polynomials. So if I say that this is the limit as x goes to minus infinity, just look at the leading terms. So minus 3x to the 5th over 4x to the 4th. And again, we're not saying that these functions are equal. We're saying their limits are going to be equal. So reducing this ends up to be minus, let me erase that and get that limit in there. So we're saying that the limit as x goes to minus infinity and then this would reduce to 3 over 4x. Okay, just changing it around a little bit. So if I look at this, what happens to this as this decreases without bound? Well, we can sketch this quick, and if I make a quick sketch, try that again. If I make a quick sketch, that's a line that goes through the origin with a slope of negative 3/4. So it's going to look something like this. Okay, so as I go more and more negative, what's going to happen to it? Well, it's going to actually increase to infinity. Now, the other way to determine this is, well, you know, it's a polynomial that has a degree 1 and a negative coefficient, so we can go back and use that same table. Okay, so that's a brief rundown on rational functions. And then the last type of limit at infinity is if we look at, say, two other kinds of functions. The only ones that we really have studied in depth are trig and exponentials. In general, trig functions will not have a limit, so we will say that their limits will not or do not exist, and I'll highlight that. So they will not exist because the functions will oscillate. They can, on occasion, converge. And when we say that, when there is a limit, we say that it converges. If it does not have a limit, then we say it diverges. Okay, and then for exponentials and logs, they are inverses of one another, and they both do approach positive infinity. It's just with a log, it's really, really slow, and it looks like a square root, but it does increase to infinity. But that's just the basic ones. Remember, we can have transformations. Alright, so remember, with limits at infinity, the key idea is look at the end behavior of the function. Polynomials, there's a table. Rational functions, there's a set of conditions that you have to check. And so that's a brief rundown on limits at infinity. And so in the next video, we will look at limits at a specific point.